Okay. So, yeah. So last time what we did was we saw some. Okay, sorry. Before even getting into the technical details, so uh, I mean, so this week, last week there were some constraints on my end because of which we had to reschedule it today. But from I mean, the next tutorials will be on Fridays only. So next tutorial is on upcoming Friday, 6 p.m. to 8 p.m., and we'll stick to it unless there are some constraints. Okay. So what we did last time was we defined what are graphs, and we saw some algorithms on it, some basic DFS, BFS algorithms, and yeah, and then we saw the running time of these algorithms. We also saw what is called topological sorting. Okay, and what we'll do now is we'll uh, we'll sort of take it to the next level. By that I mean all the graphs that you saw so far, uh, uh, and what was common in them, you had some vertices and you had some edges connecting it. So for example, you might have seen this example in the class that, let's say, A is a city and B is a city. Let's say there are some few cities, and you draw an edge whenever there's a path that connects. By path I mean there is some road connectivity from, say, B to C. There's no direct road from, let's say, C to D, but there's a road from E to D, and then say C to E, something like that. So this is something you have seen so far, where you have vertices and then you draw edges whenever a certain condition is met. But what we're going to do, so these kinds of graphs are called unweighted graph, where um, okay, let me just admit people. Okay, so these are unweighted graphs, where all I care about is that there is an edge between two vertices or not. I don't have any value associated with it. But let's say I start writing the distance of this path from A to B. Let's say that costs uh, yeah, sorry, if somebody was speaking, I could not hear. Okay, so yeah, so now let's say I want to add more information into it. So let's say if I want to go from city A to city B, then it say takes me 5 hours, and by, say, scooty, or I mean some vehicle that is common across all. Let's say from B to C it takes you 2 hours, and from C to E it takes you 1 hour. So okay, so now what, sorry, yeah, so now what we're doing is we are adding some weight to the edges. So the general instance of graph that you have seen so far was of the following kind. Whenever I tell you a graph, I tell you the vertices and the edges. Okay, and now these are the unweighted graphs that you have seen. How do I represent a weighted graph? So G has vertices, it has edges. Additionally, it has a function W which tells you the weight. So what does W look like? It takes edges and tells you what is the what is the weight of that edge associated with it, associated with the edge. So okay, uh, yeah, and then you can also have the other variant where you have some direction. So let's say these are all one ways. So there's a one way from A to B, say there's a one way from B to C, and so on. So you can have directed and undirected variants of the weighted case. So both are valid. Okay, so the point I want to make here is that there are lots of examples that you come across in real life which can be formulated in terms of graphs, and most of the time what will happen is you'll end up associating weights. So this is very natural to happen. So any example you think of and try to convert it to a graph, most frequently it will happen that you'll have some sort of weight that is associated with it, naturally. So now that now that we have these weights, there are some natural questions that arise. So for example, if I had uh, let's say one few more, let me just add few more edges, um, and let me just add some weights to it. So 3, um, let's say this is 7, and let's say this is 3. Okay, so now can you tell me how many ways are there to start from A and reach C? How many possibilities do you see?
3 ways.
Okay, what are they? Can you so one way is that you directly take this ACH. What are the other ways?
A to E and E to C.
A to B, and so I'll just write it A to C, A to B, and B to C, and
A to E and E to C.
A to E. Okay, E to C, the edge is like this.
Oh,
Okay, but you can go from E to D, and you can go from D to C.
E to C.
Okay, so now the natural question is, if I go from A to C, how much time will it take for me to go from A to C with this path?
3.
3 only. But if I go from A to B to C, then you are actually spending 5 hours here and 2 hours here, so that gives you 7. And if you go from A to E to D to C, what do you get?
14 hours.
14 hours, exactly. So notice that when we did BFS and DFS, we only cared about whether it is possible to reach from A to C or A to D, or whether there is connectivity between two vertices. That is all we cared about. But now that we have these weights, there are a whole lot of questions that arise, which are natural and which have applications which are used day to day uh, in real life. So I'll tell you shortly where. But before that, so now we saw that there are, in this case, there are multiple paths that are possible from A to C. So my job is to find what is the fastest way to reach there. Okay, so then what I'll have to do is I'll have to go across, maybe one obvious solution would be go across all the paths and find their weights like we did just now, and then find the minimum one, uh, and then take that path. Okay, so this is what is called the shortest path algorithm. I mean, this is uh, the shortest path problem, which says that, okay, which says that I give you a graph which is weighted, and you have to tell, and I'll tell you two vertices S and T, and you have to find shortest path from S to T. Okay, so you can think of the trivial algorithm, and what will happen is, in the worst case, when the graph is like really large, and you'll have to go across all possible paths, which is just a brute force, right? You want to do better. We like we have been saying since the beginning, we just want faster and faster algorithms for solving the problems. And uh, okay, and one algorithm that we know um is what is called is an algorithm due to Edgar Dijkstra. This is Dijkstra's shortest path algorithm, and this was given in 1962. It is an old algorithm, but it's very if you try to code it, if you try to write it, it's a very short program. But and if you look at the intuition behind it, it's also very simple. But it's surprising how it gives you better time complexity, and in fact does give you the correct answers all the time. Okay, so I'll not exactly start writing the code, but we will see this through examples. Okay, so that is one thing we will see. um, yeah. And okay, maybe yeah. Okay, so as a warm up, maybe try this question before we get into the Dijkstra's algorithm and all. So, okay, so I'll just um, read out the question. So you have a city where you have um, different streets. So this is street A, street B, street C, and so on. These are the streets of the city, and you have edges whenever there is a uh, whenever there's an intersection between two streets. So it could be something like this. Okay, and in this case, notice that we are not talking about the time or the distance of the street, how long it is. It's just that we're just drawing the unweighted version, and what we're saying is we want to test Alice is, let's say Alice is somewhere here and Bob is somewhere here. So this is a very small graph I have drawn, but you can imagine the graph could be as big as possible. Alice is on some street and Bob is on some street, and they want to meet together. So how do you so how should they start walking so that they can reach as soon as possible, they can meet at some street as soon as possible? That's the question. So can you come up with an algorithm for this based on whatever you have seen so far, maybe previous week thing? Anybody has any thoughts or ideas? I see some answer in the chat. uh, so can you explain your algorithm, maybe like shortly, some any intuition or something? uh, okay, okay, sure, no problem. Okay, so anybody else you want to attempt before we look at, maybe I'll give you a hint. So one of these algorithms that you saw in the last week for unweighted graphs, because weighted, would be sort of an overkill because we are not even dealing with that right now. So can you use some search algorithm? um, okay, so let's see. um, Okay, so let's do like a let's break it into a easier question. Let's say that Bob is just going to stay wherever he is, and Alice is going to search for Bob. So Alice doesn't know where Bob is, and she's just going to start from her street, and then she'll keep looking for Bob. So what do? You can use any of your BFS or DFS algorithm, right? Because that's what you do in the search algorithm. You are at a vertex and you want to see whether you can reach some other vertex or not. Okay, so then in this case, let's say you're doing BFS, then what will happen? We start with Alice, and then what are the next vertices that we will visit? B and C, exactly. So from that point, you look at who are the neighbors of A, and you're going to visit B and C. Okay, and we looked at B and C, but we did not find Bob there. So we continue our exploration. So from B, where do we go?
D.
You go to D. Okay, and you can keep exploring, but already you have found Bob at this point. So I mean, Alice has already met Bob, so there's no, I mean, you can stop your exploration at this point. So this is your simple BFS algorithm, and in this case the example is small, so we terminated. So I mean, we terminated very quickly. Okay, you can also do DFS for this. Okay, now let's uh, tackle the actual question. So now it takes Alice, in this case it takes her uh, 2 steps to get to Bob. Okay, but if Bob is also moving simultaneously, if Bob is also trying to find Alice, then uh, can we do better? Can I save on time, because they are parallelly moving now? So it's possible that Alice is moving towards Bob and Bob is moving towards Alice. So um, yeah. So how can we do some kind of parallelism in this algorithm so that yes, that is correct. So at some point Alice and Bob should meet. So in this case Bob was not moving, but Alice walked towards Bob. Now we want Bob also to move towards Alice and Alice to move towards Bob, so that we are saving on time. Okay, I think you probably have the intuition. Maybe you're shy or something. I don't know. So, I mean, the answer is very very natural. The most natural thing that would occur to you, which is, uh, which is that Alice starts exploring for Bob. So from A she goes to B, C, and then parallelly from here, Bob starts exploring his neighboring street. So which is B, E, and so on, and yeah, and eventually uh, in this case it's again easy because it's just one step here. But if you have a if you have a larger instance, then probably you'll sort of uh, see how the algorithms works in non-trivial cases. So okay, so that was just a warm up. I hope you can see how, it's just a warm up about BFS. So is this part clear, or are there any questions? Okay, good. So okay, so now what we'll do is uh, now we'll consider the case where you have weights. Okay, so there are weights on the edges, and right now we are dealing with the directed graph. Okay, so okay, so the question is, you want to move from A to D, and there are, like you observed earlier, there are so many paths that are possible that take you from A to D. So I want to find the shortest path, and by shortest I mean if you sum up the weights on the edges, it should be minimum quantity. It should be as minimum as possible. So um, yeah, so let's see how Dijkstra's algorithm works. We'll see this with an example. Okay, so okay, so what Dijkstra does is, you okay, so there are two paradigms of algorithms that you will see in this week. One is what is called greedy algorithm, and one is what is called dynamic uh, dynamic programming approach. Okay, maybe I'll just call it dynamic programming. This is also called DP, and you will see algorithms of both these paradigms in this week's material. Okay, and okay, so what are these strategies? So roughly, very speaking at a very high level, what greedy says is you're going to make decisions which are optimizing. So these come into picture when you want to optimize something. So let's say in this case, the quantity that I want to minimize is the distance, um, is the distance from some node to the other node. Okay, and there may be cases where I want to maximize some quantity. So for example, um, okay, so maybe like these represent your distributors. So these are some different distributors, and if you go from A to B, then you get a profit of some 10 units. If you go from B to D, then say you earn 1 rupee or something like that. So then your goal would be to maximize the earning or whatever the quantity is at hand. So there are both kinds of optimizations that are very naturally, that occur very naturally. One is to maximize some quantity, the other is to minimize some quantity, and these are the two kinds of optimization problems that you will see. And what greedy says is, okay, I want to say, in this case, let me say I want to minimize something. Then what I'll do is I'll make a very greedy choice. I'll choose something that is smallest from where I am. I'm just looking very microscopically. I'm not looking at the whole graph. Let's say I'm standing at A. Then there are two paths that are available for me. So I'll do the obvious thing. I'll choose the smallest one. Okay. So in this case, 5 is the shortest path for me. Uh, okay. So I'll travel that. Now, okay. Now what you do is from this node, you look at all the um, all the paths that you can take, and again you make a greedy choice. You take the one that that's the smallest for you. Okay, so it's not obvious, right, why this should work all the time. So such kinds of strategies where you just microscopically, at one step at a time, you're just choosing something that is like most profitable for you, may not always work, but there are some cases in which it surprisingly works, and we need to prove why it works. So uh, yeah, so we'll see more about this with this example, but I just wanted to give like a high level idea of what it is. So that's going to be the main idea. So what you do is you write the vertices that you have. In this case, you have 5 vertices, and uh, initially we will assume that, so my goal is to start at A and I want to reach at D. So initially what you'll do is you'll assume that the distance from A to B is infinity, infinity, infinity. That means at the moment I cannot reach any of them. Then in the next step, I'll choose one edge and update the distances accordingly. So how does that work? In the next step, amongst the two paths that I have, I'll choose the one which is the smallest weight. So what is the distance from A to C now? So what is this quantity now?
5.
5. And okay, and this is 10. I'm just updating. Okay, this is not necessarily the smallest value, but we are just updating one step at a time, and we still can't reach D because we have only taken one edge, so we still can't reach D, and we still can't reach E. So these are still infinity for us. Now in the next step, the question is, which path do you choose now? Okay, so there are many possibilities. You can either go from B to D, you can go from C to B, or C to D, or C to E. So what Dijkstra says is, amongst the distances that you have so far which are not yet visited, so A is something that we've already visited. From A, I took this path and I'm done visiting. From C, now I have two choices. Either I can let me just color it. So A is something I've already visited. Now I can either go from B or I can go from C. So what you'll do is you're going to choose the one which is uh, nearest to you. In this case it is C, so we'll start our exploration from C. From C there are 3 edges that are going, so okay, this should not be 0, maybe okay, let it, fine. So which one do you choose between CB? Maybe we'll just update it. Okay, so okay, so now what are the new distances? From A you can go to C, from C you can go to B. So what is the new weight of this path from A to B?
8.
8.
8, and it's smaller than 10, so we will write the smaller value. So this is 8, this is still 5, and what are the other values? How about C to D and C to E? Okay,
It's
so now
14.
that is correct. So from A you can go to C, and from C you can go to D. That is how we started. So what is this weight? This is 5. In C to D it is 9. So this is 14. And what about A to E? From A you can go to C, from C you can go to E. So what is the weight?
5.
5.
Sorry. Okay, so now we've visited C, right? So I'll mark this with yellow, and now the question is um, which path do we take next? So from B you have okay, so you have okay, so you have B, you have B, you have D, and you have E. So amongst these, E is the one that has the minimum distance. So you will start your exploration from E. Okay, so what are the weights now? 0. Okay. 0. So from, if you visit E now, what are the, how do you update the distances? So from this is still 5, this is still 5. So now there is a new path from A to D, which is the new path is 5 to 8.
11.
Exactly. So you have A to C, C to E, and E to D. So what is the total cost of this? This is 5 plus 0 plus 6, which is 11, which is smaller.
11.
Sorry.
11.
No, why is it 7? You're going from A to D, right?
11, no, not 7.
11. Okay, sorry. Okay, you're correct. So this is 11. And from E, there is no direct path to B, so we will not update this. So this is still 8 for us. And now we've visited we've visited E as well. Okay, and yeah, and now I mean the next smallest vertex that you have is D. So is B, because you have 8 here and you have 11 here. So you will choose the one which has the smallest distance so far. So from B, if you start your exploration, how does the weight change for the rest of them? So this is still 0, 5, um, 5. So does anything change? There is a new path from A to D now, which is A to B and B to D. So what is the cost of this? This is still 11, which is not smaller than what we had so far, so we'll just keep it 11. Okay, and now we stop our exploration. We have visited all the paths, and we've found the shortest one. So the minimum path from A to D here is that of cost 11. But now I don't want to just tell you what is the value or what is the minimum distance. I want to give you the path. I want to tell you explicitly what is the path. So how can we change this algorithm slightly to output the path also? So does everybody agree that this algorithm uh, gives you, I mean, minimum the shortest path?
Ma'am, the shortest path is 9 units, I think.
From A to D.
Yeah, A to C,
Oh,
then C to
A to
B, then
C.
B to
Okay,
D.
okay, okay. I think then there's
5 plus 3 plus 1.
something that we did not update, I guess. Uh, this was for A. This was for C. Okay, okay, okay. I think at this point we did not update. At this point we did not update um, the A to B, A to C, and C to B path, right? Um, is that clear to everyone? So what happened is from C there were paths from C to B, C to D, and C to E, which is what we did not update at that time. So this would be 8. Is that fine? Um,
Yes, ma'am.
okay. So maybe we'll just do it one more time from here. Okay. Mm, okay. So initially you started with A and you updated this to 10 and 5. Now you're going to visit C, and from C you now have a new path from A to B, which is 5 plus 3. So this is smaller, so you update this as 8, and you have a new path to D, which is 14, new path to E, which is of weight 5, and now we're going to uh, choose the next smallest one, which is E. Okay, and from E, how do the distances change? So this is 5, this becomes 11, because now you have a shorter path like this, and here you have 5 still, and there's nothing to B that we have discovered, so this is still 8. Okay, and now E is also visited and C is also visited. So now we have B and D which are not visited, and which one do we choose? Between 8 and 11, 8 is the smaller one, so we will start our exploration at 8. So from B there is a new path to D, which is of weight 1. So you have so new path from A to D is of weight 10 plus 1, which is 11. um, sorry 8 plus 8 plus 3, 8 plus 1, which is 9, and yeah, I think E is not reachable. So you will stop your exploration uh, and stop at 9. So okay, sorry that we missed this edge at the time. Sorry about that if it caused any confusion, but is it clear now? Are there any questions?
No, ma'am.
Okay, thanks. So
Clear.
thanks. So how do we how do we find the path now? This just told you that there is a uh, some shortest path of distance 9. Okay, so there's a very simple clever trick that you can do, which is that every time you update your distance, so every time we are getting better and better distance. It may improve, it may not improve, but at least it won't go below what you've currently written. Every time we do that, we will store where that distance came from. So how do we do that? So let's say initially you visited A, and we got a distance of 10 from A to B. Okay, so what was the previous vertex that, I mean, just the previous vertex that you visited? It was A, and when you go from A to C with a distance of 5, the just previous vertex that you visited was A, and for these we don't have anything because they're not reachable at this point. Next, when you visit E, what happens is you updated this path, right? You updated the value of B. So what was the vertex just before you visited B?
Ma'am, can you repeat the question?
So what we're saying is that there is a new path from A to C and C to B that we discovered. Okay, which is of smaller weight than we previously had. Previously we had 10. So I want to store, whenever I'm changing the value here, I'm changing 10 to 8, I want to store what is the previous vertex that I visited. So when I took this path, what is the vertex that I visited just before I visited B? That is C, right?
Yeah.
Okay, so we will store C here. Okay, we will update this as C, and for A, for C we only came from A, so it remains A. Now we have this distance of 14. So what is that path? That path is this, right? So you have A to C and C to D. So what is the vertex that was visited just before you visited D?
C.
C. And what about E? When you took
C.
again C. Okay, so how does this change in the next step? So in the next step you discovered um yeah, just a second. Yeah, so in the next step you discovered this vertex B, and you took this particular edge, right? So the path that you had was this, and you made an update here. Is that right? So you had 14 earlier, but now you have a smaller path of 11, so you changed that 14 to 11. But before when I changed this, what was the vertex I visited just before? It is B. It is this B that's okay. So okay, and yeah, and then in the next step what we did was we started our exploration from um, yeah, I think we started from B, and we visited this okay, maybe I did something. Okay, fine. Okay, maybe I'll sorry, this is 11, this was 11, this was 9. Okay, what happened here was okay, just a second. um, yeah, so this exploration that you did, this is from E, right? So this comes from A to C, C to E, and E to D. This is the path that gave you 11. So before you reach D here, the vertex that you visited last was E, and um yeah, I think it remains the same. For the rest of the things remain the same. Okay, and now this is the step where you start exploring B, and yeah, and now you um discover this edge B to D. So before you reach D, the last vertex that you visited, that was B, which is what you explored here. So you're going to change this to B, C, A, C. Okay, so now what you'll do is you'll read this backward. That means I got my minimum distance to D, that was of length 9. What was the vertex that I visited just before I visited B? Visited D, that was
B.
B. B. And you asked the same question for B. So for B, the minimum distance that I have was of the minimum distance from A to B is that of 8. What is the vertex I visited just before I visited B? That was C, which is what I've stored here. So you write a C here. Now you work backward again. So what is the minimum distance from A to C? That is 5. Okay, and how do I get that? Before I visited C, just before that I visited A. So I'll write A here. So yeah, so and that was your source point, and this is your target point. So you can track back one step at a time and find out your path. So basically what we did here was, I mean, although this was a bit clumsy, but basically what we did was, whenever you are exploring, let's say you started exploring A, whenever you update it, you're just going to write A. For then you started exploration for E. If at all you updated, sorry, for C, and if at all you updated the distance, which we did here, here, and here, we are going to write C there. Okay, then we started exploration from E, and I updated the distance from 14 to 11 here, so I'll write E here. You're just going to write the same vertex, because I mean, so it's not something you have to explicitly find out. And then you started from B. From B you updated this distance, so you're going to update the vertex name to B here, and at the end of it you will just trace it backward. So from D you went to B, for B you went to C, and from C you went to A. So that's it. So that was a simple trick to find out the path explicitly. Okay, so okay, so and just to I mean, philosophically it's greedy algorithm for us. I'm not formally defining what greedy algorithms are and so on, but philosophically it's greedy for us because at every step we did like um, a very greedy choice of always choosing the shortest, next shortest possible uh, path or edge, and we kept on doing it, which works for us, which is I mean, you'll have to prove it. Okay, I mean, just writing an algorithm doesn't mean it is correct, so there's something called correctness proof, which I'm not sure, I think it was probably done in the lectures, I'm not sure, but you can even look up there's a simple, okay, not simple, but there's a not so difficult proof of why this works, because someone will have to prove, right? Why should I trust Dijkstra's algorithm, and how do I know it's always going to give the shortest path? So there is a formal way of proving that it will always give you correct answer. Okay, which we'll not do right now, but the point of this was just to demonstrate how the algorithm works. Are there any questions about this? Okay.
No, ma'am.
Okay, thanks. So we'll move to the next question. Okay, so you have a simple, I mean, by simple, I mean, you have a small graph here, and now you have negative weights also, okay? So if I ask you what is the shortest path from A to B in this graph, then what would be your
Two.
answer?
-2.
Mm, how do you get -2?
A
A
to
to
C,
C,
C
there
to
is
C to B.
Uh, what, sorry, A to C,
C to D.
C
C
to
to
D,
B, ma'am. B, ma'am.
it's
and
it's 1.
okay, so you are saying 1 because you can go A to C, C to D, and D to B. So you have 3 plus 1 minus 3, which is 1. Can you do better? Can you see a smaller? Can you see a smaller path? Okay, so how about I go from A to B, B to C?
Ma'am, can you repeat the target vertex? Then A to B, B to C, C to D, D to B.
Yeah, A to B, B to C, C to D, and D to B. So by paths, we don't mean simple paths in graph theoretic sense. It's okay to visit that vertex multiple times. That is fine by us. You can even visit it as many times as you want. Okay, so in that sense, so whenever we're talking about shortest paths here, we are yeah, I mean we can repeat the vertex multiple times. So A to B, B to C, C to D, and D to B. So what is the cost? What is the cost of this?
-5.
Yeah, this is -5. So again, my question is, can you do better?
A to C, C to B, ma'am. -2.
A to C, C to B. C to B is not a path. It's B to C.
Oh, sorry.
Yeah, no problem.
Ma'am, we can travel simultaneously B to C, C to D, D to B, then again B to C, C to D.
Exactly. You can repeat it again. No, there's nothing that stops us from doing that. So you can go A to B, B to C, C to D, D to B, and you repeat that cycle again. Go to C, go to D, go to B again. Then what is the cost you will get? You will get -5 plus 1 -3. What is this? This is -12. Okay, and you can do it again, you can do it one more time, and you can keep on doing this. So what is the minimum distance, minimum cost that you can get?
-infinity.
-infinity. So you can get it arbitrarily small. Okay, so the point is, okay, why are we doing this, right? So okay, so two things to note. One is the you all might have used Google Maps at some point, and and of course you use it because you want to go from one place to another, the shortest way possible, the shortest distance or time possible, which is not necessarily the same as distance, because sometimes you look for traffics and congestions, and then there are lots of other factors that are there. It's more complicated than that, but in the implementation of the algorithm, they do use Dijkstra's algorithm to find the shortest path. Now, by there could be different definitions of paths. It could be minimizing time or whatever, but the algorithm that is used at heart is Dijkstra's algorithm. And why negative weight? So in terms of distances and times, it's I mean, you don't have negative, you don't say, I mean, you don't have negative weights, but in lots of formulations of lots of other problems, when you formulate it as graph instance, it's this negative weights naturally come up. Okay, so yeah, okay, so I mean, so just to give like just to give an example, it could be the other example that we considered. So let's say you want to um, I mean um, you want to sell, maybe you're a salesman and you want to sell your stuff. So you're going from one place to another. So this is maybe like the cost that you spend in going from one place to the other place, but this could be like an incentive you get. So maybe if you visit this particular store, then maybe there are some incentives you get, and that's what this minus thing represents. It's something that's beneficial to you to do. So I mean, there are many other natural instances where you will come up with this negative weight. So these are unavoidable. And what happens if you use Dijkstra's algorithm here? So if you try, think of this as your source and think of B as your destination vertex. If you apply Dijkstra's algorithm, then what would it give you? So maybe let's do that. So you have A, B, C, D at this point, and initially none of them are reachable, but then you are going to start your exploration from A. So how do we update? How do we update the values?
A to B is 2 and A to
A
C
to B
is
2.
2, 3,
3.
infinity.
3.
Then what do we visit next according to the algorithm?
B2.
B. Exactly. We choose to explore from B because it is smaller. I mean, the distance 2 is smaller than 3. So we start our exploration from here. And then once you do that, you're going to update this to -3, and this is still infinity. In the next step, you will visit you will visit D, and then you will change this to -3, -2. Okay, and you will terminate because according to the algorithm, we visited A, we visited B, then we visited C, then we visited D, and then we will terminate, and your answer will be that shortest distance from A to B is 2, which is not correct, which is what we saw here. So why did this happen? Do you see why Dijkstra's algorithm failed here? So the moral of this example is that you cannot use when the graph has negative weights. Okay, so so do you see where exactly did the algorithm fail? Why did this happen?
Cannot revisit the vectors.
Exactly. So the problem is that once you have visited it, you cannot update the uh, update the distance to that vertex, and you already thought that B uh, was your next vertex to start your exploration from, and you then cannot ever come back to B and change the distance. But why is it okay when there are positive weights? Okay, so the idea is that from B you have spent some amount of some cost to reach to B. Okay, now if you travel further from B and if you ever come back to B again, if at all there is such a cycle, then um, it will only increase the weight. It can only increase because all the weights are positive. If you sum up all these all these costs, they are either zero or positive. So that extra path that we are adding can only increase the cost of your path. It cannot ever decrease. In this case, it's decreasing because you have negative weights that are allowed. So sorry, so that's the reason why you can it works very well if the graph has only non-negative weights, but you can't use it for negative. Okay, so is this point clear? Are there any questions?
No.
Okay, so there is one comment in the chat which says there was this comment regarding the correctness of the greedy algorithm, right? So okay, so I'll just give you a very high level idea of what happens. So you do this proof inductively, that is, you show that at every step, if you are only allowed to, so let's say at this step, if I'm only allowed to visit these two vertices, then this is the optimal distance that I can get. At the next step, if I'm only allowed to visit these three vertices, then these are the optimal distances I can get. So finally my statement is, what would that be at the end when I visited all the vertices? It would be, if I'm allowed to visit all these vertices, then these are the optimal, these are the minimum weights, minimum cost that you will get, which is what I want to prove. So this is an inductive statement. You show that if it is true for this step, then it is true for the next step, and so on. If at all, if you are familiar with induction, you think of this as your base case, which is trivially true, and then you show it inductively that if it is optimal for step I, then it is optimal for step I plus 1, and hence you conclude that it is actually a correct answer. We will do one proof. So this is how you can prove for Dijkstra's. There are other greedy algorithms also that we will see, where you don't need induction. You can just do proof by contradiction or something like that. Okay, so we will see one such proof. We'll do, maybe for MST we will do one, but that is just to give you idea. And if you want to check it out, then Corman and um, Kleinberg-Tardos, these are the two textbooks that have maybe Katie's, yeah. Okay, so there's a chapter on greedy algorithms where you will find this shortest path example, and they're formally proved why this is correct. You can also maybe see online if you're interested to check out. Okay, so okay, so I'll just maybe okay, maybe in interest of time, maybe I'll do the spanning tree examples first, but let me just say something shortly. So this is this example that we saw of Dijkstra's algorithm. What it does is, I'll tell you a source, and it will tell you, let's say A is the source. It will tell you its optimal distances to all the other vertices. So from S, if I want to reach any other vertices, this is telling me the minimum, the shortest path. Okay, but if I want to find out, let's say, from all sorts of, I want to find from A to B what is the shortest path from A to C and all the way up to A to F. That is something you can do. Then I want to find B to A, B to C, and so on all the way B to F. And I want to find for all pairs. So if there are n vertices, there are n into n minus 1 by too many pairs, and I'm interested in finding all of them. Then what will you do? Like, what is, let's say you only know Dijkstra's algorithm, then what is the most natural thing to do? Is the question clear? So
No, ma'am.
yes. Yeah, there's some
Yes, ma'am.
yeah. Do you have any, do you have a suggestion? How do we proceed? Okay, so let's say I want to find A to B, A to C, and all the way up to A to F. Then what I'll do is, I'll run my Dijkstra's algorithm, run Dijkstra with A as your source node. If I want to find from B to all the other vertices, then I'll run the algorithm again, but this time I'll make B as my start vertex, and same thing, you keep on doing this, and finally for F, you make F as your source. Okay, so how many times did I have to run the algorithm? If there are n vertices, how many times
All the vertices are completed.
sorry, I couldn't hear you.
Until all the vertices are covered with covered.
Yeah, so there are n vertices, so we do it n many times. Okay, so that means you've done n times, you've run Dijkstra's algorithm n times. Okay, and let's say yeah, so so this algorithm, you can show that this runs in time order n square, although we did not do it, but with yeah, it's not very difficult to see. Once you write the code and if you analyze it properly, you will see that this turns out to be order n square. This is something we've done in the lectures. So then what is the total running time if I have to find all pairs of shortest paths? What is the total running time for this? So for every vertex we are running it once. It took order n square time here, took order n square time here, and so on for each of the columns. So there are n many times you run it. Each time it takes order n square.
Order of n cube.
Exactly. So it takes order n cube time. Okay, but the problem is that I can't run this if there are negative weights. Like we discussed, it can happen. It can so happen that there are negative weights. Then my Dijkstra's algorithm doesn't give me the correct answer all the time. So then what you do is you use what is called Floyd-Warshall algorithm. This is also called all pair shortest path algorithm, which is also called APSP as an abbreviation. Okay, and if we have time we'll discuss this. It's a very intuitive algorithm. So it uses what is called dynamic programming approach. Okay, so it's like thinking of the big problem as sub problem and finding your final solution using these sub problems, like finding optimal solutions for sub problems, using them to find optimal solution for the bigger problem. Okay, so it's a very very nice idea. Okay, so if we have time we'll discuss this, and the running time of this is also order n cube, but it's a one shot algorithm. You don't have to run it multiple times like we did for Dijkstra with A as source, B as source, and so on. It's just a one shot algorithm, and it will give you shortest path for all pairs of vertices. And the advantage is that it also works when there are negative weights. So this works when there are okay, so if there is time we will come back to this, and the next question is also related to that, so we'll do it after we're done with this. So now we'll move on to the second problem that is very natural. Okay, so it's called minimum spanning tree problem. Okay, so so what is a tree? We had discussed this last time. So okay, just give me a moment. I'll plug in the charger. Okay, sorry, just give me a moment. I think I'll have to share the screen again. Okay, Yeah, sorry about the disturbance. Okay, so anybody quickly, what how did we define tree? Yeah, uh, how did we define the tree? Okay, so tree was basically acyclic connected graph. And what do we mean by that? If you just see this picture, you'll probably recall. So you have a vertex, then there are edges that give you a new set of vertices. Then there may be some edges that give you new set of vertices, and it keeps on expanding like that. So you can't have edge from here to here, because that will create a cycle and so on. So this is how we define tree. And now, yeah, so I mean, this was the case when you don't have any weights, like we discussed. Now the whole theme of this week is when you have weights associated with it. Okay, so let me let me just draw a simple diagram. So okay, I'll call this A, B, C, D, E. Okay, do you see a tree inside this subgraph? So if I delete some edges, I'm allowed to do that. Then can I get a tree? Can I obtain a tree from this graph? If yes, then can you tell me what edges are to be deleted, or maybe just tell me the edges in the tree? Okay, so is this a tree? I take this edge, this edge, this edge, and this edge. So these four edges, do they form a tree? From A, you go to B, you go to C, E, and in the next step you have D. This is a tree, right? Because
Yes.
I can't add any more edges to it. If I add any more edge, let's say I add B to E, then I create a cycle which is AB, BE, AC, which is not what I want. Okay, do you see? This is just one tree that is sitting there. There are many others. Can you see some other tree?
A to B, B to C, and A to E, E to D.
A to B. Sorry. Can you repeat again? Sorry.
A to B, B
A
to
to
C,
B, B to C,
A to E,
A to
and
E,
E to D.
and E to D. Yeah, that is another tree. And you can always ask how many trees are there in this particular graph, or in general, if I give you any graph, then what is the maximum number of trees and all. Okay, I mean, all these are some nice combinatorial questions that you can ask. We'll not get into it, but the point we want to make is, now let's say there are weights to these edges, and okay, so let me just randomly write something. So this is 9, 6, 4, 3, 2, this is 1, and let's say this is 7. Okay, then now there are weights to the edges. Then what is the cost of this tree? What do I mean by cost? You look at all the edges of this tree and add their weights. So this is 2, this is 1, this is 9, this is 6. Okay, so what is the weight of this tree? I'll call this T1. What is the weight of T1?
18.
8. Oh, sorry,
18.
18. Yeah, this is
18 no?
18. Good. And what about this one? So here you have 2, 9, 3, 6.
20.
This is 20. So weight of T2 is 20. So which is smaller? Clearly T1 is smaller. So yeah. So now like some of you have tried to count the number of the possible trees that I mean all possible trees that are there. So the natural question that we want to ask is, what is the minimum such tree what is a tree whose edge cost of edges, if you add, you get the minimum number as possible. So this is similar to the shortest path question, where you were interested in finding the shortest path among all paths. Here you want to find minimum cost tree among all possible trees that are there in the graph. Okay, so yeah, again, very natural brute force trivial algorithm would be that you find out all possible trees and you add their costs, and then you find the minimum one and output that, which will take really bad time. It's a very in terms of running time, it's a really bad algorithm. Okay, so I want to do something better. Okay, so there are two algorithms that are really simple to state. Again, if you try to write their code, it will be very small, and both of them have a are from the same paradigm. Both of them are greedy algorithms. So you'll see two more greedy algorithms. One is due to Prim's. So Prim's MST. So we call this minimum spanning tree. Sorry. Okay, or it is also called MST. And second is Kruskal's MST algorithm. Okay, I mean. And why is it called minimum spanning tree? Tree is definitely because you are looking for a tree. It's spanning, meaning you have to have all the vertices in it. You can't say that, okay, this is my tree A, B. See, this is also a tree in the graph, but this is not what we want. I want all the vertices to be there. I want D to be there, I want E to be there. So hence I'm forced to add some edges. Okay, so spanning means all vertices should be there, and minimum meaning you want to find the minimum cost. If you add the edge widths, then you want it to be minimum. So this is what you mean by the minimum spanning tree. And so both of these are greedy strategies, but both are different, and if there is time we will see proof of correctness for this. Okay, so again, like, best way to maybe describe the algorithm would be that we run it on an example. Okay, so we'll run it on this example and see what do the algorithms do. Okay, so we'll just state the idea. So we'll first see Kruskal's algorithm, and yeah, so what you do is you look at all the edges that are there. You can even imagine that you have sorted them already. Okay, and sorted them in ascending order of edges. So if you sort them, what is the minimum weight edge that is there in the graph?
1.
1. So what I'll do is I'll be very greedy. Okay, I'll say that this edge has to be in my tree. So CF, this is already there in my tree, and now I want all the other I want to include all the other vertices. Now what you do is think of this edge as if it's not there in the graph. Just think that it is deleted. Now in the remaining edges, which is the smallest weight edge that you can see,
A to A.
A to B, yeah, AB.
A to B or A to E.
Yeah, you have choices. So for now, let's say we will randomly, arbitrarily take anything. Okay, so let's say I take AB. Okay, now imagine that this edge is also deleted. Then what do you choose?
A to E.
A to E. So you do A to A, and imagine that this is also not there. Then what do you choose next?
A to
C.
C.
A to C. So you add this edge and delete this. What is the next edge that you see which has minimum weight?
A to F, but it creates a cycle.
Exactly. So the next edge that you see, which has minimum weight, is E to F. But I can't add this, because the moment I add this, I would have created this cycle, which is not what I want, because I want a tree, not a cycle. So then just forget this
A
edge.
to D more.
Sorry, what did you say? B to
B
D.
to D.
Yeah, that is correct. So we'll just cross off this edge also, because having this will also create this cycle. And again, the next smallest is 5, but again this will create a cycle, so we will discard this off. And like Karthik said, the next smallest is 7, so I'll add 7, and it does not create a cycle. I'll add 7. What do I do next?
D to G.
A to G.
D to G. Good. So then we go D to G. This is 7, this is 9, and yeah, we discarded this, we took this. Okay, so if you add all the all the weights, what you get? You get 24. Okay, so the minimum spanning tree, yeah, so the minimum spanning tree in this graph has a weight of 24, and once its spanning tree is this, there could be multiple spanning trees which have the same weight. So for example, in this particular example itself, what we did was, first we chose CF, this is 1. Then instead of AB, let's say I would have, let's say I chose AB, then I chose AE. Then I had two choices, which was either to take AC or to take EF. So let's say I take EF this time. Okay, now I can't add this, I can't add this, I can't add this. Then I'm going to choose, I think, yeah, I'm going to choose this again and this again. Now if you add the cost, what do you get? This is 9.
24 again.
This is again 24, but both are different trees. Okay, so it's possible that there are multiple MSTs which have minimum weight. That is okay, you just have to output one of them. Okay, so this is Kruskal's algorithm, and of course I think you can see why this is greedy. It's greedy because you're just getting the minimum edge each time, as long as you don't violate the tree property. And again, we need to prove why this works. Okay, this, I mean, we don't just buy algorithms like that. Okay, and we'll, if there's time, we'll get there. But the second, let me just quickly demonstrate the second algorithm. Okay, so it's called Prim's algorithm. And other thing is, we want to understand what is the running time of this. So for that, you need to, one thing that is there is, you have to sort the edges, because every time you're going to take the next minimum edge. So how much time will sorting take? You've seen in the first week, I guess, you've seen different sorting algorithms, right? Bubble sort and selection sort, merge sort, and so on. So how much time does it take? Okay, so in general, if I give you an array of size n, and I want to sort it, then sorting would take me order n log n time. This is if you use merge sort or if you use quick sort, either of these. But if you use, say, selection or insertion or something, you will end up taking quadratic n square time. Okay, so yeah, anyway, so in this case, what is n for s? What are we sorting? We are sorting edges. Okay, so there are size of e many edges. So how much time this will take? This will take order size of e times log size of e. So this is only due to sorting. Okay, sorting itself take this much time. Additionally, you will end up spending more time in checking whether it creates a cycle or not, and so on. So that will add up to the running time of this algorithm. But you have to choose data structures cleverly, so that you can, if you choose a good data structure for this algorithm, you can do better. You can do like yeah, we'll see that. So next week material is about this union find data structures and I think pointers and so on. So yeah, so in the next week we will see how do you implement this. So if you just do with arrays, you'll end up spending a lot of time. So there are clever ways of doing this. So we'll see implementation in the next um, tutorial, which is on Friday. Okay, so right now we'll not discuss the implementation part, we'll only see the algorithm. Okay, and now let's see the Prim's algorithm. Okay, so what does Prim's algorithm say? um, okay, so what does it say? It's slightly different strategy. What it says is, you start with, first step is let's say the same. You start with a random vertex. So let me choose A for now. You can choose anything. It is okay to choose any vertex, because eventually that vertex has to be in your tree. You can't not have one vertex in your tree, right? Because you want a spanning tree. So I'll just randomly choose A, let's say. And now, how many edges, I'm going to choose one edge that goes out of it. So just a second, let me admit someone. Okay, so now there are 3 edges that are going out of A. Okay, and I'm gonna have to choose at least one, because otherwise if there is no edge that goes out of it, then it will be disconnected from the rest of the tree. So that's not the definition of tree, right? It is a connected graph, so there has to be at least one edge that goes out of it. So I'm going to choose at least one. So again, we are being greedy, so we'll choose the one which has minimum weight. Okay, so in this case there are 2 3 3 2 3 and 2. These are the weights. So what will you choose?
A to B or A to E?
A to B or A to E. So let's say I choose A to B. Okay, next what I'm going to do is, I'm going to think of this as my subgraph, as my subgraph, and look at all the edges that are going out of A as well as B, and then choose the minimum out of those. So right now we chose this. Now you will look at all these edges, 4 edges, and choose the minimum out of those. So what is the minimum? Next
A to
minimum,
E.
A to E. So you go A to E, which is again 2, and you remove this. Now you're going to look at all the edges that go out of B, A and E. So E, A and B, which is the minimum?
E to C or E to F.
A to C or E to F. So let's say I choose this. Okay, and now you're going to choose, look at all the edges that go out of B, C, E, A, and choose the minimum of that. So what is that?
C to F.
C to F. Next, what do you choose?
B to D.
You choose B to D. Why is that? Because I cannot take this, it will create a cycle. I cannot take this will create a cycle, and similarly this will create a cycle. So I'm going to choose this, and that will give me, yeah, that will give me D. And then next, what do we do?
D to G.
D to G, which is 9. So what is the total cost of this tree?
24.
24. Again, the cost of, I'll call this tree T3, and the weight of T3 is 24, which is same as what you got earlier. Okay, so again, same thing happens. Okay, there were some points where you had multiple choices. You could have chosen this, or then you had a choice for this or this. So depending on what choice you made, you might end up getting a different tree. So that is fine, because there could be multiple ones. So yeah, so the other thing is that, again, you might have by now noticed the flavor of this algorithm, which is again that you are making greedy choice. Earlier you were making greedy choice based on the edges in the whole graph, which are not still used. But here the strategy is different, but it's still of greedy kind. You start at a vertex, you look at all possible edges that go out of it, choose the minimum one. Then you keep growing your tree. From the partial tree that you have created, you always look outside and choose the one which is minimum weightage, as long as it doesn't create cycles and so on. Okay, so one difference in terms of implementation that this has is that you don't have to necessarily sort this, because I'm not looking at all the edges in the entire graph. At any point, I'm only looking at what goes outside my partial tree. Among those, I'm choosing. So I don't have to sort that. That would be like overkill. But as the tree keeps growing, there are lots of edges that we are looking at, and we have to choose each time what is the minimum one among them. So again, you need like a good implementation, a good data structure, so that you can do this quickly. Again, we'll not see the implementation of this, but that we'll do in the next um, tutorial. So yeah, so the point of this was just to tell you the working of the two algorithms. Okay, so are there any questions about the two algorithms, any of the two?
No.
Or okay, good. So then let's try this question. Okay, so
Ma'am, what is the time complexity of these algorithms?
yeah, so that depends on what data structure you are using. I think so for Kruskal it's something like order e log e, because the sorting takes a lot of time. um, so for Kruskal I think it's I mean it's e times v. I don't exactly remember, but yeah, but both of them have different complexities. So we'll discuss this next time when we actually see the data structure that we're using. Okay.
Okay,
uh,
ma'am.
okay, so yeah, so look at this question. uh, what the statement says that G is some connected undirected graph, and you have edge costs C of E associated with every edge, and assume that they are all distinct, so you don't have two edges with the same weight. And let's say E star is the one which is cheapest in that. Is it necessary that every minimum spanning tree must contain that edge? So for example, in our case, we had this edge which was, in this case we don't have distinct, but assume that all of them are distinct, and then this is the cheapest edge. So look at this spanning tree MST we constructed. It has this edge CF, this also has the edge CF, and this also has the edge CF. So the question is it necessary that this minimum weight edge must always be there in any minimum spanning tree, or is it possible that there is some counter example you can come up with?
Ma'am, if A to B and B to E, there is A to B and B to E, B to C. Uh, the weight of A to B is 2 and B to C is 3, and uh, A to E is 9 and E to D is 1. So we can connect C to D instead of E to D.
So you are saying not this but this.
Yeah, ma'am. And the
Okay,
weight is like 1 or 2, 3, 1, 2.
okay. This is the graph that you are giving, right? Or
Yes,
is
ma'am.
it okay? So there is only one tree in this, which is the graph itself. I mean, the graph that you have given itself is a tree. Um, is that fine?
Ma'am, C to D is 1 and E to D is C to D is no, sorry. Yeah, E to D is 1 and C to D is 2.
Two you cannot have, because this says distinct costs. You
Oh,
cannot have two edges with the same cost. Is this fine?
4. We can take 4.
4, okay.
So if we create a tree, then we no need to include the E to D edge.
Um, no need to include the E to D edge. So you're saying this edge is not there in the graph, or what? You are saying that this is the tree.
Yeah, this is a
This
tree.
is the tree. But then, what is the cost of this tree? 9 plus 2 plus 3 plus 4. That is 13 plus. That is 18, right? So if you go E
We can
A,
remove the A to E also, no?
you can remove the
E to A.
B to A. So then you are saying this is the tree. Uh, is that what you're saying? You're saying this is the minimum spanning tree.
No, ma'am, E to A, ma'am.
E
E to
to,
A, 9.
okay, this you
A
remove.
to E.
Huh. Then you have this tree, but then that satisfies your claim, right? It says that the minimum cost edge, which is ED in this case, is there in the MST. So, uh, so you're getting this, right? So what we're saying is it always the case that no matter what graph you take and no matter what minimum spanning tree you take in that, it will always have to have this minimum weightage? This is the claim. The question is it true or not? Okay, so if you want to disprove it, then it is enough. You can give me an example like this and show that okay, there is this MST where minimum cost edge is not there, and I'll be convinced that okay, my claim is false because you gave me a counter example. But if I want to prove it, then I cannot give you an example like this and say that in this case there is this MST and it has this minimum cost edge into it. Hence, it should be true for all graphs and for all MSTs, right? Because it is true for this case. That is all you are showing. So if you want to prove it, you have to prove it in general. You have to argue in general why this is true. Is that making sense? Like why this example is not enough? Are there any doubts? Then please let me know. Okay, sorry. Just give me a minute. I need to charge my um, laptop. So in the meantime, please think about what I said, okay? And let me know if you have doubts. Just think about what I said just now. Um, yeah. Uh, okay. So, is are there any questions about what we said just now? Uh, can you, I mean, does this make sense? Please, I mean, let me know if it does not, I can repeat it. Okay, so maybe I'll explain the answer and then you let me know if it does not make sense. Okay, so the answer for this claim is yes, it is always true that for all graphs, for all MSTs of the graph, the, let's say the minimum cost edge is E star, then E star has to be it has to be in the minimum spanning tree. So how do we prove this? Okay, so we can prove this by contradiction. Okay, so let's say suppose not. Okay, suppose this is so is everybody familiar with proof by contradiction? Have you seen it sometime, or if not, then please let me know.
No, ma'am.
Okay, so okay, so this is called proof by contradiction, and what you do is you want to prove something, right? So generally what you do is you do direct proof. You assume this is true, hence something else is true, hence something else is true, and you conclude what you want to do. So if you do something like that, it's called a direct proof, because you're just making direct conclusions from series of statements. But what does proof by contradiction say? It says that you uh, you want to prove something. In this case, I want to show that every minimum spanning tree in every graph must contain the minimum cost edge. So I'll assume that it is not true. Okay, so which sounds weird if you're uh, thinking about it for the first time, but let's see how it works. Okay, so you assume this is not the case. So what does that mean? That means suppose there is an MST T which does not contain E star. Okay, using this fact, I will arrive at a contradiction. By contradiction, we mean something which is, something you assumed earlier, but now you are saying that is not true. So that can't be, you can't say this happens and this does not happen at the same time, right? So that is what a contradiction is, which we will see in a few steps now. Okay, so let's say this T does not contain E star. What you do is you look at all the edges of this tree. So you have given me some tree, these are the edges E1, E2, E3 and so on. There are some edges. Okay, what you do is you sort the edges in the ascending order and you give it to me. So for this tree, let's say E1 is greater than E2 greater than E3, or ascending order maybe. So, and let's say En. Okay, so okay, so notice that there cannot be any equalities here, because we assumed that all the edge weights are distinct. You can't have two edges that are of the same weight, so they have strictly ascending order. Okay, so now I'll construct one more tree. Okay, I'll modify this tree. This is the tree that you gave me, and I will add this edge E star. So okay, so now is this a tree anymore?
No.
No, right? So then what I'll do is, I have added this E star, I'll remove one more edge. So why am I doing that? Because this is creating a cycle, right? So I'll remove some other edge. So let's say I remove E3 from this. So what does it look like now? There is E1, there is E2, there is E star, but there is no E3. This is what we deleted, and the rest of the edges are the same. Okay, now is this a tree?
Yes, ma'am.
This is right. You can also prove this using the exercises that we did last time, that the number of edges in a tree is if it's n minus 1, and so on. You can use those to prove formally, but we'll not do this right now. Intuitively you are convinced that this is a tree. Now the question is, I'll call this t prime. What is the cost of t prime? What is the cost? It is cost of t plus I added E star to it. So I am paying E star, but I also removed E3. Okay. So is this greater than cost of t, or is this smaller than cost of t? Or what can you say about this?
Less than
Less than cost of t.
Exactly.
Less
This
than
is
question.
less than cost of t. Cost of, yeah. So that means T prime should be an MST, right? T cannot be an MST because for it to be an MST, it has to have minimum weight. But there is some other tree T prime which has weight smaller than that T, then T cannot be an MST. Is this fine?
Yes, ma'am.
Right. So that means T is not an MST. But you started with this assumption that T is an MST. Okay, so this is the contradiction. So this is what I was saying that time. You assume that your statement is not true. This is what we did. And then eventually you make some series of arguments. Eventually what you will end up with is a statement like this, which is contradicting some statement that you have made in the past. In this case, the statement which is being contradicted is, first you started by saying T is MST, then you did some jugglery here and said that oh, T is not an MST, which cannot be true at the same time. So then you arrived at a contradiction, and hence you say that your assumption was false. So why did this happen? Because what you assumed was not true at all, and therefore this assumption is not true. Hence for all graphs G, for every MST, the minimum weight edge E star must always be in it. So for those of you who are seeing this kind of proof for the first time, is this clear?
Yes, ma'am.
Okay, good. So yeah, so you can think about what will happen when I allow equality. In this case we assume distinct edge costs. Let's say I allow you to have equal edges. Does the same statement hold? You can think about it. uh, Try this out. Okay, I have maybe we can do one more question quickly. Okay, so the I'll read out the question. Okay, so you have been given a graph G, all of whose weights are positive and they are distinct, like we said earlier. Okay, and T is some minimum spanning tree of this instance. Now what I'll do is, so let's say this was my G, where you had like 1 7 8 9 5 2 3, something like this. Okay, so what I'm going to do is I'm going to change this G prime by squaring all the edge widths. So this becomes 1, this becomes 81, this becomes 64, 49, 4, 9, 25. Okay, so basically you just look at an edge width, square it, and write that as your new edge width. Now let's say there is some minimum spanning tree here. So yeah, can you quickly tell me a minimum spanning tree in the graph G? You can use Prim's algorithm or Kruskal's algorithm, whichever is easy for you. So you take this minimum weight edge, you take the next minimum, next minimum, next minimum, and next minimum. So is everybody convinced this is an MST? Okay, so what is the cost of this? Cost of MST here? is
18.
18. Okay, so now what I'm saying is I'll take the same edges. Okay, I'll not apply any algorithm on G prime. I'll just blindly take the same edges. Sorry, this edge, this edge, this one, and this one. Now the question is this tree? Of course, it's a tree because we have not changed the structure of the graph. It's a spanning tree. Question is it minimum spanning tree in this graph now that the edges are squared?
Yes, ma'am.
Yes. So why is that? Can you like come up with the argument or some kind of proof? If you have some starting thoughts also, partial thoughts also, feel free to share. Okay, it need not be correct all the time. Okay, we'll come to the proof of this. We will prove this, but before that, let's ask the same question for shortest paths also. Okay, so instead of minimum spanning tree, what you do is you have a graph, you have some shortest ST path, you take a G prime where the weights of edges are squared again. Okay, and now uh, the question is that shortest path still a shortest path in the graph, in the new graph?
Yes, ma'am.
Yes, ma'am.
Okay, why do you think so? Okay, so my answer is um, I mean, I disagree with you on the second answer. So for the first one, I'm saying yes, this is correct. For the second one, I'm saying this is no. And when you understand why it is true for A but not for B, you'll see you'll see the how the structure of one algorithm is different from the other. You'll see uh, some details, some intricate details inside it. Okay, so let me first show you why B is not correct, because for to do that I just need to give you a counter example. I'll just give you one. Okay, so for B we are saying this is not true. How do I convince you? I'll give you a counter example. So what is my example? It's a simple graph. Say A to B. I have um okay, I have a path of length 4 5 D, and let's say I have 7. Okay, so what is the shortest path from A to D in this graph?
A to C and C to D.
A to C and C to D. What is the cost of that?
8.
8. Now you square this. So this becomes 25, this becomes 16, this becomes 49, this becomes 1. Now what is the shortest path?
A to B, B to D.
A to B, B to D, right? So now do you see that this contradicts the statement, right? At least that much does everybody agree that the same ST path is no longer a minimum cost path. Does everybody agree with this?
Yes, ma'am.
Yes, ma'am.
Okay. Okay, so um, now what we need to do is we need to prove that it is true for A. Okay, because if I don't prove this, then somebody may come up with a counter example and say that, oh, your claim is not true. So for A we will give a proof, for B we already have a counter example. Then you'll see why why does this happen. Like, it's very non-intuitive, you won't expect this, but you'll see why this happens. Okay, so um okay, so what I'll do is I'll simply apply my your favorite MST algorithm. So let's say I apply the Prim's algorithm. Um, let's say I apply the Kruskal's algorithm. What it does is it takes the minimum age and picks it into your tree, assumes it is not there, then takes the minimum age among the remaining ones, takes it into your tree, and keeps on doing it until there is no cycle. Okay, so then uh, what happens is here, let's say, uh, I mean, you look at any two edges, okay? So here, let's say I look at this and this. So 1 is less than 7, okay? It respects, when I square this, it's going to respect that ordering. So if 1 is less than 7, then 1 is also going to be less than 49, because you know that if you know this fact that A is less than B implies A square is less than B square. This is something you know, right? So if I sort these edges, okay, that means A, B, C, D, E, F, let's say I write them in sorted order, that is AB first, then CD, then what ED, DE, then EF, BC, BF, and AF. Okay, then without even running a sorting algorithm on this, you can see that the ordering of these edges is going to remain the same, because of this fact that if A is less than B, the square is also going to respect that. So this is also going to be the same ordering. Okay, so now what happens is, now I'll run my Kruskal's algorithm, and whenever it chose AB, it is going to choose the same edge here, and then it's going to choose the next minimum, and so on. So everything is the same, only the weights have changed. And whenever it so happened that some edge here created a cycle, that same edge is going to create a cycle, and you're going to discard it for the same reason. So yeah, so for that reason, when you run the Prim's algorithm, it's the Kruskal's or Prim's algorithms is going to follow the exact same set of steps. So do you buy this proof? Does everybody agree with this? Okay, so now you're convinced that it is true for A, it is not true for B. So can you see what is that one step which made this not work in the algorithm, the Dijkstra's algorithm? Let's say if you analyze what happens. Okay, so I'll just try to give you one explanation. Let's see if that makes sense for you. Otherwise, you can think about it on your own. But yeah, I'll just try to convince you why this happens. So one thing here is that the algorithm follows the exact same steps. But when you do this for the Dijkstra's algorithm, what happens is you let's say you start your exploration, and you went from A to B, you went from A to C. Okay, and then uh, yeah, and then what you are actually doing is you are checking if the AC square plus CD square is greater than or equal to AB square plus BD square. That is what you're doing, right? So you are basically checking if the weight of this plus new weight of this plus new weight of this is greater than or equal to the new weight of this or new weight of this. But AB plus CD greater than sorry, AC plus CD greater than AB plus BD does not imply that if you take individual squares and sum them up, then it will preserve the order. So in this case, it so happened that you didn't add anything, right? Prims and Kruskal, they don't add and check any cumulative distances. It just picks, either you pick or you leave. You don't do this kind of calculation, you don't do this kind of changes and try to find smaller and smaller at every point. So it is because of this fact. So earlier you were checking whether the sum of these two distances is greater than these two distances. Now you're checking whether squares of and sum of squares is greater or not. So yeah, so it's because it fails here, this is not true. That's why you can come up with a counter example like this. So I don't know if that makes sense, but does it make sense to you? Hmm.
Yes, ma'am.
Okay. So um, yeah, so I think I'll conclude the tutorial for today with this, but there are few more questions that we could not try today. So uh, try to solve it. If you have any questions, then you can ask in the next tutorial, or you can even mail me or something. So yeah, so I hope this, I mean, what we discussed today was helpful. If there are any doubts, you can ask me right now. I mean, regarding whatever we discussed today. Yeah, and next we will meet on the upcoming Friday, same time, 6 p.m. to 8 p.m. So I'll stay back for a couple of minutes if you have any doubts. And um, okay, do you have any homeworks? Okay, I'll try to add more questions to this. If you want more, then when I upload this PDF in the drive, I'll try to add more of them. You can attempt this, but a good source for finding questions to solve is Kleinberg Tardosh. So uh, the book has a good number of solved as well as unsolved examples. Sure, sure. So yeah, do refer to the book. Okay, so some of these examples are in fact taken from the book. So yeah, if you want more, you can always try there. If I have more questions, I'll add it to the PDF before um, yeah, before publishing. Okay, so yeah, how was the difficulty of this tutorial? Did the questions moderate, easy, or any feedback? Okay, so yeah, so thank you all for attending. I'll stop the recording. I'll upload this on the same playlist on YouTube. You can watch it if you have, I mean, if you want to go back to any of the discussion points. Okay, so thank you all.
Thank you, ma'am.
Thank you.